In this video, we're going to talk about what happens if you look at an object through multiple lenses, 2, 3, or more. Well, the basic idea is that you end up seeing still some final image, which is to say that if I took two lenses and looked at somebody's face through those two lenses, I would still see their face somewhere. It may be bigger or smaller at a different location, it might be flipped upside down, but you'll still see some image of it. The question then becomes, how do you find that image? Where is it, and how large is it? Now, we just need a very simple generalization of the tools we already have. And the idea is that you'll use the image of the first lens as the object of the second, or the image of the second as the object of the third. So you just take the image from your last lens and then apply that as the object of your next lens. And the order of the lens, first, second, third, means the order that the light travels through. So the first lens would be the lens that the light from the object first hits, and then the second lens would be the next one that it hits, and so on. And the reason why this is true is that the light, after it goes through the first lens, acts entirely as if it went through, like it came from the image from that first lens. So it wouldn't matter if the light actually came from an object at that location or was merely the image of another object. And you can use either the thin lens equation or ray tracings to find the location of the second lens. You just now entirely ignore that first lens. Once you've found the first image, you ignore the object that created it and the lens that created it, pretend they don't exist, and now act as if that's simply a new object. If you're going to use the thin lens equation, we need to measure these distances appropriately. So even though physically the first image is the second object, here I'm going to call the object distances O sub 1 for the first object, or the lens object for the first lens, and O sub 2 is the object for the second lens, and so on. Physically, I1 does not often equal O2. The reason why is that even though they're physically the same object, the distance I1 is measured from the first lens. So how many centimeters is the first image from the first lens? And then this O2 is the measurement of how many centimeters the first image is from the second lens. So even if you have the same location, you're often not equally distant from both lenses. And then what you do is, having had these, having labeled these different image locations, you can either do a ray tracing twice, as I mentioned, or you can do the thin lens equation twice, just with each lens done separately and using the I1, O1, the notation I've shown here. The magnification is a little bit easier. You can actually do this in one step. And the basic reason is, if the first image is, say, 3 times larger than the object, and the final image is 3 times larger still than the first image, overall, the final image is 9 times larger than the object, so just simply weasing it through it. You just have to multiply together to the two magnifications. So you can just write down a single equation for the magnification pretty easily, where you just multiply the individual magnifications, negative I over O, for both of them to find the overall magnification. Now, there's no such easy rule to do to combine the two thin lens equations, but physically what you do is you usually have, say, the first object distance and the first focal length, then you find I1, you look at the diagram, having known I1, you figure out what O2 is, now you have O2 and F2, often you find I2, and that tells you the location of the second image, which in this case would be the final image. It tells you where it is, and then you use the magnification equation, now knowing I1, O1, I2, and O2, plug those in, and then find the overall magnification to find how large it is. Now, the one thing I would caution you about is that you can have the unfortunate or confusing case where the first image actually forms to the right of where the second lens is. Now, in the thin lens equation, that's actually very easy to do. That's when you use a negative object distance. So for example, if it was over here, say 5 centimeters to the right of the second lens, O2 would equal negative 5 centimeters. And then you can carry out your equations as normal and it's appropriate. I won't give you the ray tracing rules to use if your first image appears on the wrong side of the lens, so to speak.